Good afternoon, everybody. So today is a grand finale, and I hope to deliver as promised. I apologize for stealing time from your recitation class, but today we have just 3 quick exercises, and I really want to come to a punchline because I really would like to start the next semester as promised from Leavitt path algebras. So I hope to finish the story of pure graphs in this semester, which means in this lecture. Okay, so now we are ready to bundle up the 3 properties: hereditary, saturated, and unbroken. And we need these 3 things to define the concept of admissibility and strong admissibility, which is absolutely crucial for Leavitt path algebras and for graph history algebras. So here it goes. We start from a definition, building up, of course, on our previous definitions. Okay, so we call a subgraph E inside F admissible whenever it satisfies the following 2 conditions. The first condition demands that if I take all vertices that are missing in F0, so I subtract from the set of all vertices in a bigger graph vertices in a smaller graph, so the set of all removed vertices, so to speak, must be both hereditary and saturated. Okay. Next, there's an arrow condition, and here I have to pay attention to a subscript. So when I look at all edges in the smaller graph, it must be equal to the preimage, but it's important, preimage under the target map of a big graph of E0. Okay, so if I would write here T subscript E, that would be a tautology, right? It's obvious if I have a map from E1 to E0, then preimage of the whole target is the whole domain. But the thing is that here I'm taking the preimage with respect to a bigger map, to a map which is from F1 to F0, okay? So the point is that when I restrict the targets of TF to just E0, then the preimage must be equal to E1. Why F0? No, I didn't miss anything. No. No, you see, this is, you see it, F1, E1, and it goes into F0, E0, okay? And TF is between big sets. TF is from F1 to F0. So when I restrict myself here, I take the preimage, it must be equal to this subset. Okay. So that's exactly as written. Okay. By the way, please use a mic when you speak, because otherwise people cannot hear you. That's they hear me, they don't hear you. Okay? Yeah, I know, it's not obvious, but we don't have so many cordless microphones. I mean, it's also cordless, but you cannot wear it on yourself. Okay, but that's not the end. This is just a very basic definition, but we want more. We call an admissible graph, an admissible subgraph. Strongly admissible if, in addition, it satisfies the property that the subset, let me just write it down, F naught less E naught is unbroken. In F. Okay. So this is very important to have these two layers, and I hope you will see next semester why it is important to make this distinction. And we'll have plenty of examples just after this definition. But just remember that being admissible means hereditary and saturated plus the arrow condition, and strongly admissible means hereditary, saturated, unbroken, and the arrow condition. Okay. But I want to finish this definition with two more items in the vocabulary, because it's really convenient when you speak about it that you have some shortcuts. So now I also want to define admissible intersections and admissible unions. So furthermore, we say that the intersection graph, say F intersect G, is admissible and let me do it in one go, respectively strongly admissible whenever both inclusions, so F intersect G, included in F, and F intersect G included in G, are admissible, respectively strongly admissible.
Excuse me?
Yeah?
Could you remind me what is unbroken?
Just a second, yes? Okay. Yeah, surely. All right, but just to finish the sentence, instead of saying, all right, so the intersection is admissible subgraph in F and the intersection is admissible subgraph in G, I just say that the intersection is admissible. Okay, this is just vocabulary. Before, it's a genuine definition. This is an extremely important concept. And below is just notation, if you want. And just to answer your question, the concept of being unbroken of a breaking vertex is the following. You have the set of all your vertices, and here have some subsets H. And a breaking vertex for H in a given graph is a vertex with a property that it shoots infinitely many arrows into H and finitely, but not zero arrows outside of H. Then if such a vertex exists, you call it a breaking vertex. So say that the set is unbroken if there does not exist a breaking vertex. That's the concept, okay? And I want to finish this definition, so much in the same way. We say that the union say F union G is admissible respectively strongly admissible whenever both F viewed as a subgraph if in F union G and G viewed as a subgraph in F union G are admissible respectively strongly admissible. Okay, so this is a board long definition, but I suppose that's the only definition for today. And this is very important. I would like to alert you to the fact that the concept of admissibility is well known. This is in textbooks, except that it's called in a strange way. They say, instead of saying that E is an admissible subgraph of F, people write that E is a quotient graph of F, which for me doesn't make any sense because the quotient that you get is a quotient of algebras, not of graphs. So this is the kind of terminology I strongly oppose because it's conceptually wrong, even though it's written in books. But you have to be aware that if you look at the literature, this concept is known under the term of quotient graph. E is a quotient graph of F if it satisfies these two conditions. Okay? All right. I mean, and it is confusing because it's not like you take the set of vertices and you shrink it to something. No, you don't shrink anything, you remove it. You're talking a subgraph. The quotient that you get is at the level of algebras. Okay. And now this concept of strong admissibility, I haven't seen it. Just like this concept of being unbroken, I haven't seen it. The concept of breaking vertex is, of course, well known, but I haven't seen anybody using the term unbroken for the set as I just defined it, and strong admissibility, but it is really very useful when you consider Levitt path algebras and graph C-through algebras. So who cares if it exists or not, we introduce it, okay? At least I'm not aware of any conflict of terminology. Okay, so now examples and counterexamples. So first, well, I know I do it all the time, but so you might get bored with these graphs, but I view the circle graph as a subgraph in the Teplitz graph. Okay, I like it because it corresponds to the famous symbol map from the Teplitz algebra to the circle algebra. And so here what happens, I need to here put some names to make sure we're on the same page. So this is a vertex V, this is a loop E, this is again a vertex V, and this is a loop E. So you see how this inclusion works. I mean, here it's unambiguous, but in some other graphs it might be not so clear. And this is, if you want F included in G. And what have we got here? So if I look at, oops, sorry, it's E in F, let's be consistent. I use F and G for intersections and unions and E in F for subgraphs. Okay, so first, if you look at the set we're interested in, this is equal to what? F naught has these two vertices and E naught has just one vertex, which is equal to W. Yeah, and this is both hereditary, saturated, and unbroken. I mean, the graph is row finite, so everything is unbroken, right? Because look, if you don't have an infinite emitter, every set is unbroken because there's no breaking vertex, because there's no infinite emitter. So here everything is automatically unbroken, but it's actually everything. It's hereditary, saturated, and unbroken. Hereditary, saturated, unbroken. And right, well, it is obviously hereditary because it's a sink, W is a sink. This is saturated because the only other vertex emits one edge outside of W. And we already said what is unbroken. So finally, we just have to observe that this condition taking the preimage under TF of E naught, and E naught just consists of one vertex V. And we look in the graph F, which arrows and in V. And there's just one arrow, one edge E. Okay, so this is equal to one element set E, but this is precisely E1. So the condition is satisfied. So conclusion, strongly admissible. Next. So this is circle in the disk, and now have a disk in a sphere. So I take my Teplitz graph, and I include it in the Podlesh equatorial quantum sphere graph. And here I have to put some labels. So I call it V, W1, E, G1. So the loop is E as before. This is G1, this is W1, this is G2, and this is W2. So I put it as the left leg, okay? And this is again my F, E in F. So let's look what happens here. We have F naught less E naught. This is just equal to W2. And of course, it's unbroken because this graph is rho finite. Now, is it hereditary? Yes, because it's a sink. Is it saturated? Yes, because W1 is a sink. And wow, I should also, yeah, I named this vertex V. Yeah, because W1 is a sink and V emits an edge which doesn't end in W2. So it's hereditary, saturated, and unbroken. Now, how about the edge condition? So the preimage on the F of E naught. This is the preimage on the TF of these two vertices, W1 and V. So what ends in W1? G1. And what ends in V? It's E. So it's G1 comma E. But this is precisely the set of all edges in E. So this is equal to E1. So again, the conclusion is it's strongly admissible. Okay. So far, so good. Now, how about admissible and strongly admissible intersections? So we'll look at the intersection F intersect G, which I pictorially write in the following manner. So this time, I instead of writing just the symbol of infinity, I label the edges to make sure that it's clear that they are really distinct sets. I have countably infinitely many edges. I label them as xi, I running the natural numbers, which go from my vertex V to vertex W1. And I intersect this graph with a graph which has countably infinitely many edges. I label them as y, j. J also runs natural numbers, and it goes again from the same vertex V. So these two vertices are the same to some different vertex W2. Okay, so that's my intersection. And of course, the intersection is just a simple graph with no edges and one vertex V. Okay, and now let's see. And then you should remember that if I take the union of such graphs, I have exactly this weighted complex quantum projective space. The two quantum spheres that are attached at the North Pole or at the pole. Yeah. So this actually has a geometrical meaning to have the union of these two graphs. Okay, so let's see if it's strongly admissible. Well, I claim is strongly admissible, this intersection. But now I have to be careful because this is not the raw finite graph, so if it's unbroken, we have to pay attention. But it is strongly admissible because Well, and I have to show that the inclusion of F intersect G into both F and G is strongly admissible, but here the situation is completely symmetric. So if I convince you that the intersection is strongly admissible in F, of course, it's also strongly admissible in G, because this is a completely symmetric situation. Okay, but let's write it down. So there are two reasons why it is strongly admissible. So first, both F naught less G naught. I can write F naught less G naught intersect F naught, but it's the same as F naught less G naught. And this is equal to W1. And G naught less F naught. Again, you should read it as G naught less F naught intersect G naught. But it's just short to write it like this. And this is equal to W2. They are both hereditary, saturated, and unbroken. And let's check that it's really true. So I look at W1, and I look at it in the graph F. And this is hereditary because it's a sink. It is saturated because there is no regular vertex outside of it. This vertex is an infinite emitter, so saturation is okay. And it's also unbroken because yes, it does emit infinitely many edges into W1, but it doesn't emit anything outside. And the same, it's completely symmetric, okay? So this is condition number A. And condition number B, so this is this edge condition. So you have to verify it. So now I have to write down the intersection. So T F, the preimage of under the TF of F naught intersect G naught. So F naught intersect G naught is just the V. And I look into the graph F and see what ends in V. This is nothing, it's an empty set. And likewise, symmetrically, when I look in the graph G, then the preimage under TG of F naught intersect G naught is again an empty set, because there is no edge in G ending in V, and there is no edge in F ending in V, so these are empty sets. But this is all right, because this is equal, in both cases, this is equal to F1 intersect G1, right? The intersection of these two sets is empty. So we have this edge condition satisfied, so it's claimed this is strongly admissible, okay? This intersection is strongly admissible. And let me make a spoiler. The goal of today's lecture is to prove to you that if the intersection is admissible, respectively strongly admissible, then so is the union. This is the main theorem for today. And it's the main theorem the whole semester, to be honest. Okay, but let's do some more examples and counterexamples. So I have one more example. So this time it will be a situation in which the intersection is admissible, but not strongly admissible. So you see that one has to distinguish between these two. And when doing this example, I'll try to explain what difference does it make at the level of graph algebras, whether something is admissible or strongly admissible. Okay, so this is my example number 4. I take the intersection F intersect G. So this time, well, it's something very similar to what we had before. but this time I added a loop. Okay, so again, I have V. I have countably infinitely many edges going from V to W1. But I also have a loop, call it E, at the vertex V. So it's no longer a source. And I intersected with a symmetric graph. So I have countably infinitely many edges going from V to W2. I label them by Y, so Yj, with J running natural numbers. But I also have a loop, the same loop E, over here at V. Okay, so now it's obvious that the intersection graph is the circle graph. And I claim that this is admissible, but not strongly admissible. Okay, let's check it. And again, here situation is completely symmetric, so I can write both. So this is, yeah, I have again two reasons, right? A. Both F naught less G naught and G naught less F naught are hereditary and saturated. But they are broken. But broken in F and G respectively. Okay, let's verify it. So again, as before, F naught less G naught is W1 and G naught less F naught is W2. When I look at W1, of course, it's hereditary because it's a sink. Now, when it comes to the saturation property, again, there's no problem because by adding a loop, I didn't change V to be a regular vertex. It's still an infinite emitter. So saturation is okay. So these two check out. But why is it broken? Well, it's exactly broken because of this loop, right? Because this is what I was explaining to Xiao, right? We have a case that I have infinitely many arrows shooting into my subset, but there is one arrow which goes outside, which is emitted from this vertex and does not end at this subset. That's exactly what is not allowed, okay? And let me also quickly check the edge condition. So the edge condition works because when I look at the preimage of the intersection F naught G naught, well, this time is no longer empty, but it will just have a loop, okay? So this will be one element set consisting a loop because F naught intersect G naught is just V. And the only edge ending in V is the loop E, okay? And it's the same when I take the preimage under TG. All right, and this is okay because it is equal to F1 intersect G1. This is just with one loop E. So F1 intersects G1. So it is admissible because these two subsets are hereditary and saturated, and the error condition is satisfied. But it is not strongly admissible because we have a breaking vertex, okay, for these inclusions. And now, how does it matter? You see, in a way, it's really more important to be admissible than strongly admissible, because you still will have a map, right? Remember that whether you're doing Leavitt or graph-sister algebras, doesn't matter. Let me write it in terms of graph-sister algebras. When I have an inclusion E and F, which is admissible, so I'm making a spoiler for next semester, admissible, this implies that I have a star homomorphism from C star of F to C star of E. And of course, you can do the same at the Leavitt path algebra level. Okay? So it can be broken. Even if this inclusion is broken, it's still no problem. Yeah, you still have such a map. But the upshot of being strongly admissible is when the ideal, because these are surjections, right? I mean, you are identity on generators that remain, and you annihilate all these generators which are killed, which means vertices beyond E naught and all edges which end beyond E naught. So these are generators you kill, everything else survives, and you can wonder what are the ideals, okay? So that is an ideal generated by the projections if F naught less E naught, if strongly admissible, and more complicated otherwise. You have to add projections which are not given by vertices.
Sorry, I have a question.
Sure.
Is this idea also a corresponding C-star algebra of a graph? Maybe a subgraph of F?
No, I'm not sure. I don't think so. I mean, first you are here already in the non-unital setting, and you have to be careful not to. It's a little bit like when you think about the following situation. I have a compact set, which is a subset in a bigger compact Hausdorff set. Okay. So then I have a continuous map from the C-star algebra of continuous functions on L onto continuous functions on K. And now I can look at the ideal of the surjection, right? And these are all functions vanishing on K. But you no longer can describe it, you know, as of course it is a C-star algebra. It is an ideal, and you can say, fine, well, these are functions vanishing at infinity on L minus K, right? Because now this is a locally compact Hausdorff space, and you can say, wow, so when I take the ideal associated to it, I take functions which vanish at infinity on such a locally compact Hausdorff space. So yeah, I mean it's but I don't know what happens here. You see, but you have distorted functoriality, because here I write this ideal. Okay, I can write it indeed as say C naught of L minus K, but I don't know how to complete it here. What do I write? L minus K. What is this map? I'm not sure. But it's a good question. This is a good question, and possibly in some simple cases, you might have it that this is a graph algebra of a graph, but that's not what is important here. So it's a good question. I'm just give you an analogy, and you can explore it in this fashion. I'm not saying no, I'm not saying yes, but what I'm saying and emphasize is that the only thing that is spoiled by the lack of strong admissibility, once you have admissibility, is that your ideal is no longer just generated by the missing projections. You need to add additional projections. You can understand why, because you see, look here. imagine that you now kill W1 and you kill all Xi's, right? So before V was an infinite diameter, there was no Kunz-Krieger relation. E was just an isometry. We had that E star E was equal to the, well, I should write it, partial isometry associated to E times partial isometry, partial isometry associated to E star, and partial isometry is equal to projection associated to V. But because this is an infinite diameter, there is no relation the other way around. It's an isometry, partial isometry, not the unitary. The moment I kill W1 and all Xi's, I have a Kunz-Krieger relation which tells me SE star is PV. So then it becomes actually unitary because PV becomes 1. Okay? And this is the projection, this is a relation which you didn't have before in your graph. So this means that you have to introduce more relations. This means that you have to add more generators to this ideal. And this complicates some proofs. Okay? But you can live with it. I think your life is getting more complicated, but I believe you can still achieve similar or the same results depending on the situation. Okay, so this is why we bother to distinguish between admissibility and strong admissibility, just because we have a different description of ideals when you go to the world of graph algebras. But this was just a spoiler for the next semester.
Piotr,
Yes.
what was the purpose, or what is the purpose of admissibility only?
The purpose of admissibility is that you have a morphism. You see, when one of these two conditions of admissibility fails, I mean, whatever, if it's not hereditary, if it's not saturated, and if the arrow condition fails, then you simply don't have a map. There is no star homomorphism. It's ill-defined.
From the C-star algebra.
Well, this is a standard lemma in graph algebras. If this is admissible, then there is a star homomorphism from C star F to C star E, and likewise for
them. Okay, yeah.
So you need admissible to have this morphism.
Mm-hmm.
Otherwise, you can write, of course, your formula, but it's ill-defined. It doesn't map the Kunz-Krieger ideal to the Kunz-Krieger ideal.
Yeah. And the question was also if every ideal is a graph algebra, or
what?
What was the question? What was the question from the audience?
Oh yeah, ask it again.
I think my question is, so there is a morphism from C star algebra from C star of F to C star of E. Then my question is, if it's the kernel of this map, which is ideal, it's also a C star graph algebra. Yeah.
So if every ideal of a graph algebra is a graph algebra.
So we don't know yet.
Oh, you know the answer, Alex, right? This is a fact, right? Every ideal of in a graph C-star algebra, you say that it's a graph C-star algebra of a graph?
I'm thinking, I'm not sure.
Yeah, see, I'm not sure either. Yeah, I know these are trivial questions, but one of the reasons we having this course is that we want to learn such things.
So there's one related question, like by Sarah Ackland, like do phantom Kunz-Krieger algebras exist? And it says basically you describe your graph algebra in terms of properties, so not in terms of construction. For example, like a list of properties like real rank 0, purely infinite, blah blah blah, and so on. And then you may wonder, like if you start with a Kunz-Krieger algebra, you usually have these properties by construction, and then these should pass to ideals. And so it may not be clear if so this ideal would have this abstract properties, but it's not clear if it's a graph algebra.
Yeah. I guess we will ponder about it next semester.
So it's an open question.
Oh,
it's an open problem.
We can still think about it. Now, counterexamples. All right. So I'm doing something very similar. I'm taking the circle graph and I include it in something which looks like the Teplitz graph, but it is not the Teplitz graph. because now this additional edge, which is not a loop, goes into V. So this is, say, V, E, this is V, W, but now this edge, how did I call it? G. This goes from W to V, not from V to W. And this is not admissible, okay? So here what we have is that, of course, again, F naught less E naught is just W. And this is saturated because it's a source, nothing comes into W. Yeah, so this is saturated. But of course, it's not hereditary, because it emits an edge which leaves the subset. So this inclusion is not admissible. Okay. And this is serious. So when you have a discussion, that's some strange graph C-star algebra, and there is no star homomorphism onto the circle algebra. Okay, another counterexample. Let's take, yeah. Sure.
I have a question to this comment, but you only mean that there is no star homomorphism. Define this.
You're absolutely right. It crossed my mind. You're absolutely right, Jacek. Yes, this was slightly imprecise, and thank you for catching me here. I have two C-star algebras. This is the whole big world, and maybe I just take a zero map or something like this. So I'm just saying that the map, which is canonically defined for the inclusion, which means that we simply kill some generators while keeping the others without any change, that the map given by such a formula is ill-defined. That's all I'm saying. You're right. So the canonical, the induced homomorphism, yeah, the induced star homomorphism does not exist. That's a way to put it. Yeah. But now let's take the graph, which is a graph of 2x2 matrices, both in Levi and C-star, because it's finite dimensional. So I have two vertices, V and W. I have one edge, call it E1. And I include it in a graph which simply has one more edge. So the same set of vertices, V and W, but now I have E1 and also E2, both going from V to W. Okay, so note that here F naught less E naught is an empty set. So it is everything. Hereditary, saturated, unbroken, whatever you want. Hereditary and saturated. But the edge condition is not satisfied, because when I take the preimage under F, sorry, G, no, sorry, this is F, yeah, this is E in F, okay, of E0, but E0 is the same as F0 here. So this is everything. This is F1, and it's not equal to E1, okay? When I look at the preimage of W under the F map, then I have two edges, E1 and E2. Okay, so that's the preimage. This is bigger than the set of edges in the subgraph. So this inclusion is not admissible. And I'm almost certain that the graph algebra for such a graph, Alex, what do you think? This is just 3x3 matrices, right, Alex?
That's M2 tensor the torus.
No, there's no torus. It's not the loop. There's no torus.
So where does the I don't see the arrows going. Both arrows going.
Well, look who
W?
is talking. You remember how you draw arrows when?
Yeah.
So you really cannot complain. But I at least I said it, that both edges are going from V to W. There's no loop. It's finite dimensional.
Oh, so that's just M3.
When I 3x3 matrices, and of course there is no map. And now, Jacek, there is no map, any map, from 3x3 matrices to 2x2 matrices. Agreed? There is no such a map. Whatever. Yeah. I mean, we want it to be unital because otherwise we have a zero map. Okay. So this edge condition is serious. It's not just hereditary and saturated or unbroken. It's very important that you really don't mess up with the edges. You do not subtract the edges. You subtract the edges only when you subtract the endpoints.
But Piotr, I mean, like, you can have like I think Jacek is right. I mean, like, you can have like you may have some sort of subgraphs that do themselves not embed in the canonical way, but still embed into the other one. So I'm like simply saying like so it's really only about the canonical lift.
Yeah, but this is what we already discussed. This is what Jacek
No,
had.
but I mean, like Jacek said, like I mean, like, because you say so there is no map at all. Even you say no.
Yeah. So in some cases there's no map at
But
all.
but there's maybe also some cases where it's not hereditary, but still you have maps.
Yeah. That's maybe.
So Jacek has a point.
Not easy to imagine, but I cannot rule it out. I mean, I'm not aware of such a no-go theorem, right? Here, my claim is only that the induced homomorphism does not exist. And in a special case, no unital star homomorphism exists, right? Because M3C is a simple.
I think you can easily come up with M2 goes into M4, where you have it saturated but not hereditary.
Yeah, but you still will not have, I mean, so you will have a map from M2 to M4, but then it's hard to see that you have it by subgraph. No, let's not waste time for this. This is not very fascinating because we really care here about the induced maps. Otherwise, what's the point of doing the graphs? Okay. All right. More counterexamples. Now about intersections. Okay. So now we take, so this is my third counterexample, and I take F intersect G. I write my F as a graph consisting of two vertices and one edge going from V to W1. And I intersect it with a graph where this edge goes the other way around. So it goes from V to another vertex W2, and I call this edge E2. So as before, of course, intersection is just a very simple graph with no edges and one vertex V. And this is not admissible because I have to have a bigger piece of chalk. When you look at F naught as G naught, then of course this is equal just to W1, right? This is F naught is W1V and G naught is V W2. Then this set is not saturated in F. Right, because I have a regular vertex outside of the set W1, and it maps all its edges into W1. So you see, before it was prevented, even without the loop, it was prevented by the fact that it was an infinite emit. But now this is a finite emitter, so we do have a Kunstkrieger relation, and things do not work. So this is not admissible. Although you might remark that it is hereditary because it's a sink. Okay. Now in the same spirit, but now let me reverse the direction of the edges. So I somehow take the opposite graph to this graph. So F intersect G. I have the same set of vertices W1 and V, but now my E1 maps from W1 to V, not from V to W1. And again, I intersect it with a graph where I have an edge now mapping from W2 to V. Okay, so the intersection will still be V, a very simple graph with no edges and one vertex. And this is not admissible. But now for a different reason. Because if I take F naught less G naught, which as before is just equal to W1, okay? This is not hereditary in F. Right, it's obvious because it emits an edge which doesn't add in W1. However, you might remark that this time it is saturated because V is a sink. But here still things do not work. And I have one more counterexample, but let's look what we are trying to write here. I mean, this will be the graph algebra is just complex numbers, okay? And these are 2x2 matrices. Again, there's no homomorphism from 2x2 matrices into complex numbers, okay? And regardless of how you write it here. And in fact, if it's not hereditary, you cannot even construct a subgraph by our method. Remember, once I proved the proposition that being hereditary is tantamount to our construction defined as removing the vertices and all edges that ended with vertices will not produce a subgraph. That's if and only. So here it's even worse because in this case you don't even have a subgraph. This is not a subgraph. I mean, yeah, in a way, I can say yes. It's if you think about the construction, right, of a subgraph through a subset of vertices, then this is not a subgraph. It is a subgraph in the loose sense. I mean, it is strict sense, but it is a subgraph which is not obtained by our construction. Okay. So anyway, these are counterexamples. I have one more counterexample. Now I take my intersection as follows. I have again just two vertices, V and W. But now I have an edge E1 and E2 mapping from V to W, and I intersect it with a graph with the same vertices, V and W, but different edges. I have still my edge E2, but I don't have my edge E1, but I do have an edge E3. Okay? So of course the intersection is a graph with two vertices V and W and one edge, notably E2 going from V to W. Okay? And well, this is not admissible because the edge condition is not satisfied. So when I take the preimage under TF of the intersection F naught G naught, intersection F naught G naught is of course just a V, and I take the preimage in F, and this is sorry, wait a second. No. F naught G naught is everything, you see, because F naught and G naught are equal. So the preimage under F is E1, E2. Okay, but this is different from E2, which is F1 intersect G1. Okay, so here the edge condition fails. However, you might observe that both F naught less G naught and G naught less F naught, well, everything you want them to be. Hereditary, saturated, and obviously unbroken. You're right, of course. You're right. Yeah, I was just about to say it. Yes, they are both equal to the empty set. Yeah, an empty set is everything. So you see, the admissibility can fail just for the arrow condition. Okay, there's nothing wrong with the subset, but it's empty. But this arrow condition does not allow you to claim the admissibility. And you see, again, look, it makes sense, because if you view this intersection graph as a subgraph in any of these two, again, it's like looking for a map from M3, 3x3 matrices into 2x2 matrices. It does not exist. Okay. But here I wanted to show you on the intersection, when the intersection can fail being admissible just because of the edge condition. And I think this is enough when it comes to examples and counterexamples. And now we come to the main theorem of the semester. Of course, we had this big theorem counting k paths in finite graphs with n edges, but this was more for sport and more than the result. Methods were interesting, in my opinion, but here is something which is really, in my opinion, again, fundamental in graph algebras. So if I were allowed to ask you to remember only one thing from this semester, then I ask you to remember this theorem. Okay? This is really the cherry on the cake. And except for, combinatorics of finite paths, everything else was leading to this theorem. Okay? Of course, we had this detour into combinatorics of finite paths, which has nothing to do with this. But studying finite paths will be important, very important in Leavitt path algebras and in graph C3 algebra. So having some sport with them is not such a bad idea. And now this is a new result in collaboration with a number of people. And the admissible version was published last year, and the strongly admissible version was proved at the beginning of this semester. So this is really fresh stuff. Okay, so what's the theorem of the semester? Let F and G be graphs whose source and target maps agree respectively. I'm writing it to make sure that the intersection exists. This is the condition for the intersection to exist. Okay? Agree respectively, of course, on F1 intersect G1. Okay, and then if the intersection which exists is admissible, or strongly admissible, respectively, so is the union. And I hope the logic is clear, right? What I'm saying is that if the intersection graph, which exists by our assumption, and when also the union graph exists by assumption, if the intersection is admissible, then the union is admissible. And if the intersection is strongly admissible, then the union is strongly admissible, okay? So that's what we want to prove. And, well, it takes a page to prove it. So. Well, the application is actually very important because what happens is the following. You can now look into the category of graphs, and this will be a push out in this category. And this will be a push out which can be dualized to a pullback of graph hysteralgebras. And once you have a pullback of graph hysteralgebras, the Meyer-Vittoris six-term exact sequence in K theory works. Yeah. Yeah, that's next semester. Yeah, but you're right. I mean, this is if you want prelude to a case, right? It's of course the highlight of a semester because we didn't go beyond graphs in this semester. But mathematically speaking, this would not be so exciting if it didn't bear any weight on Leavitt path algebras and graph hysteralgebras. But it does. But it does. And this is very, very general. Okay. Especially now that we also allow breaking vertices. But the pullback theorem in the admissible case was just published last year. And we are still checking, right, Alex? I don't know if Mariusz finished checking it. It's halfway done the proof that we have a pullback in the strongly admissible case. No, sorry, I think it's the other way around. Strongly admissible case is easier, so that's proven. And published, and the admissible case, which is weaker because it allows breaking vertices, we still believe that the pullback theorem works, but now ideals are more complicated. So checking the Pedersen conditions, which who Oscar was, I think, presenting, is more complicated.
But we I mean, like, we disproved it, right? I mean, like, we made this, I mean, like, the counterexample.
I don't hear you, Alex. I don't know.
Oh, can you hear me?
Yeah, now it's better.
Yeah, but we disproved it, right? I mean, like, so the counterexample with.
No, this wasn't a counterexample to this theorem. You are confusing things.
Oh, I'm sorry. Yeah.
No, that's this is a complete. You had some kind of example. It has nothing to do with this. This is a different story.
So what is?
Oh, I forgot.
Ah, okay.
No. Don't confuse things. This is.
So this theorem on the blackboard, yeah.
Yeah.
Okay.
So I definitely believe, and it's like halfway proven that, and it is supposed to be now a joint paper with Mariusz, right, Alex? Is that under the weaker assumption of admissibility, where we allow breaking vertices, okay, we still have a pullback theorem. But I repeat, checking the Pedersen conditions for the pullback is more complicated because the kernel ideals are more complicated. But at least halfway we checked it and it works. And I definitely bet that it will work completely. But you see, that's not done yet. So this is really fresh. Okay, so let's prove it. And it will take me at least half an hour to prove it. So please be patient. But I think the proof is not boring. Okay. So first, we just prove that admissibility implies admissibility, right? So let me write it like this: Fg admissible implies F union G admissible. So we do it in 2 steps. Okay. So to begin with, know the following in basic set theory, that when I look at the set I'm interested in, which is F naught union G naught, and I subtract F naught. So for instance, I want to prove that the union is admissible. So I have to prove that this subset, and the same with G naught here instead of F naught, I have to prove that both of these subsets are hereditary and saturated. And let's see what they are when you compute them. Yes?
Piotr, I think you need to state, I mean, you know that admissibility is a relative notion. So
no, not for the intersection. This is why I defined what does it mean that the intersection is admissible.
Intersection is admissible in F respect
to T. No, but I defined it. This was the reason why I made the definition. I said that the intersection is admissible of F with G.
Piotr, you calm down, please. I mean, I'm just like telling.
Yeah, but this has been defined. You see,
admissible subgraph.
Yes. Yes, so but I said that F intersect G is the intersection admissible if this is admissible in F and in G. This is why I made this definition.
I see. Okay, I see.
In order not to write it so many times. Of course, now I can say that there is some ambiguity because, of course, I can write F intersect G as F prime intersect G prime, and then this is different. Okay. So this is a shortcut, and if you want to be very pedantic, so thank you, Alex, this is a good point. I can write the intersection of F with G, of F with G. Okay.
I just didn't see the.
So it's the union of F and G. Yeah. So now now this is absolutely precise, okay? Because I'm saying that the intersection of these 2 sets is admissible and the union of these 2 sets is admissible. The operation of taking the union or the intersection of these 2 sets, and this has been defined. But it's just a shortcut, okay?
Yes, I see.
Writing too much, but thank you, Alex. This was the point was not the one you were making, but the point was related. When I write, say, F intersect G, it's just a certain graph, and it might be equal to F prime intersect G prime with F prime different from G prime, and then it has a different meaning. So strictly speaking, I'm sure George Eliot would protest, right? But now this is a way out. Okay. So now I compute it. This is, well, computed, just observe. That's just G naught less F naught, because of course, when I withdraw it from the union, F naught vanishes, and I just remove F naught from G naught. But this is, of course, the same as removing from G naught the intersection of F naught with G naught. So we see we are in the lucky situation, because whether we consider admissibility of intersection, admissibility of the union, the subsets for which we have to check whether they're hereditary saturated are the same. Yeah, this is the subset we are supposed to check to verify that F is admissible in F union G. And this is the subset we are supposed to check to verify that the intersection of F and G is admissible in G as a subgraph of G. Okay, so this is nice because this already we know that it is hereditary and saturated in G. So the whole trouble is, because you could say, well, it's trivial. This is hereditary saturated, so this is hereditary saturated because the sets are equal. But now, Alex, you should say that this is a relative, relative concept, yeah? Because here, this is hereditary and saturated in G, and we want to prove that this is hereditary saturated in F union G. And that's different. So this is why this argument is not trivial. Okay, so to begin with, we note that this is, and just as I said, hereditary saturated in G is hereditary and saturated in G. Well, because F intersect G in G is admissible. So now what we want to prove is that it is hereditary saturated in F union G. So do it. Consider an edge, E, such that when you take its beginning in the union graph, so S cup of E, well, that it begins in the set G naught less F naught, yeah, the set under consideration. Let me compress it, such that S cup of E belongs to G naught less F naught, okay? But then we know that this is not in F naught, and it follows that E must be in G1, right? Because if E can be either in G1 or in F1, that's the definition of a union graph. If E were in F1, then its beginning would be in F0, but it isn't, okay? So I can conclude that E is not in F1. Okay? But hence, E must be in G1. There's no other choice. So if I take the end of this edge in the union graph, because E is in G1, this is like TG applied to this edge. And of course, it must be in G0 less F0, precisely because this set is hereditary in G, okay? G naught less F naught is hereditary in G. Right, so we have something which starts in this set, is an edge in G1 from G1, and now because of a hereditary property, it must also end in this set, okay? All right, so we've got it. And now it follows that it is also hereditary in F union G. Let me write it down on the next blackboard. And it follows because of the way we started, okay? We took a vertex in this set, which happens to be equal to that set. And we considered an edge beginning in the set in the sense of a union graph. So we didn't say that it's in G1 or F1. We concluded it's in G1. But we took an arbitrary one that starts in this set. And then we concluded that it simply must end in the same set. So it follows that, in fact, this set is also hereditary in the union graph. Let me just write it down. follows that F naught less G naught is also hereditary in F union G. And of course, the symmetric argument will allow us to handle the situation when instead of F naught, we take G naught, okay? But before we do the symmetric argument, let's now also establish the saturation property. This is slightly more complicated, but not much. So let's do it. Next, suppose that we have a vertex V, which is in the set we are interested in. So we want to somehow assume that the logic is the following. I want to suppose that the union is not admissible, and then I want to prove that the intersection is not admissible. This is logically equivalent, okay? So I assume that, say, the way the union fails to be admissible is, sorry, I said admissible, I meant saturated. I'm looking at this set, okay? And I want to prove that if it is not saturated in the union graph, then it is not saturated in the graph G, okay? So I suppose that I have a vertex which spoils the saturation property of this set viewed as a subset in the graph F union G, okay? So it must be a vertex which is outside of this set. So I have F naught union G naught, and I subtract from this set. So F naught union G naught less F naught. But this is like taking double complement, right? The complement of a complement is the set itself. So this is just equal to F naught, right? And now I suppose that it is a regular vertex which emits all its edges into this set, okay? So let me write it down. Yeah, it's a regular vertex in F union G. This is important. It's a regular vertex in F union G, and such that when I take the ends of all edges emitted from this vertex, so T cup of the preimage of S cup of V, okay, that all this is inside F naught. Well, let me just write G naught less F naught. Right, it's faster than writing this one, okay? So I just suppose that I have a vertex which breaks the saturation property in the union graph, okay? And I want to prove that it also breaks the saturation property in G. Okay? But, well, you see, I look at the set of edges emitted from V, and they all end outside of F naught. So all these edges must be in G1, okay? They cannot be in F1, otherwise they would end in F0. So let me write it down. Then any edge emitted from V belongs to G1. And because it belongs to G1, it must start in G0. But we already assumed that V is in F0. So it is in F0 intersect G0. Okay? So here I have a nice picture, which I want to draw. Here I have F naught less G naught. Here I have G naught less F naught. Here's the intersection of F naught with G naught. And we are looking at our vertex V, which we just established must be in the intersection. And well, it emits, it's a regular vertex, and it emits all its finitely many non-zero edges into this set G naught F naught. So there is at least one edge going from the intersection, beyond the intersection to the right, to G naught less F naught. At least one, at most finitely many. Okay? So that's the picture to have in mind. And we go on. So also, because all the edges emitted from V are in G1, we can simply write that the preimage under S cap of V is equal to the preimage under SG of V. You see, in general, the preimage under the cap map is the union of preimages for the subgraphs, G and F. But because we know that here everything emitted from V is in G1, that's just equal to the preimage of SG. Okay? But this implies that V is regular in G. Right? Because what does it mean for a vertex to be regular? Well, you look at all edges emitted from this vertex, and it must be a finite non-empty set. So since these two sets are equal, in both cases they are finite and non-empty. So this means that V is regular in G. So that's important, because if you want to say that V witnesses the failure of G naught less F naught being saturated in G, well, then V must be a regular vertex in G. This is a relative concept. But we just established that it's regular in G. Okay? And now combining all of this, with the fact that when I look at TG of SG inverse of V, that's the same as T cap of the preimage under S cap of V. So it established that SG inverse of V is the same as S cap inverse of V, but you see, that's all in G1. So T cap applied to element in G1 is just TG by the definition of T cap. Okay? So these sets are equal. And well, by the assumption you see here, this is contained in G naught, that's F naught. So we now conclude that the set G naught F naught is not saturated in G. Right, so we just proved, and of course, symmetrically, we can prove also that when we look at G naught, at F naught less G naught, it will also be saturated in the union. Okay, because I repeat, the logic is we assumed that G naught less F naught is not saturated in the union graph, and it follows that it's not saturated in G. So in other words, if it is saturated in G, it is saturated in the union graph. But we assume it's saturated in G, so we conclude that it's saturated in the union graph. And now I can write this sentence that by the symmetric argument, we have established like the first condition of the admissibility. Well, let me erase the theorem. I need more space. So the conclusion of our reasoning is that thus it's G naught less F naught, yeah. G naught less F naught is saturated. It's hereditary and saturated. In the union graph, and the symmetric argument, and I use the article V because it means F interchanged with G, shows that also F naught less G naught is hereditary and saturated. In the union graph. Okay, so to finish the first part of the proof, we still have to verify the edge condition. And this is more fun, actually. Okay. So let's do it. Furthermore, taking advantage of the admissibility of the intersection viewed as a subgraph in G, we compute. And I really like this computation. So I take the preimage under T cap of F naught, and I see what happens when I subtract from it all edges in F1. I try to compute this and show that it's an empty set. Okay, so first I can just write it down as the preimage under the T cap map of F naught intersection G naught. Why? Because if I take anything in F naught which is beyond G naught, then this in the preimage I'll get only edges from F1. Yeah, because if I have an edge which did I do it correctly? Yes. One more time. Why is it equal? Well, because if I go beyond this intersection, so if I have an edge which does not end in G0, then it cannot be in G1. If it cannot be in G1, it must be in F1. So it's gone by the subtraction of all edges in F1. So I lose nothing by restricting myself to the subset, because everything beyond the subset will be killed by subtracting F1. Okay? So this is first step. But now observe that Yeah, and sorry, I should write less F1, of course. Sorry, this is important. This didn't vanish. And now I claim that I can replace T cap by TG. Well, again, you see, when I take the preimage under T cap, this is the union of the preimage under F and the preimage under G. But the preimage under F will land in F1. And all edges that are in F1 will be subtracted anyway. So I can restrict myself just to the preimage of TG. Yeah. And now, which is very important, we use the arrow condition for this admissibility. Okay. So we know by the admissibility of this subgraph, F intersection G in G, we know that this is just F1 intersect G1. So this is equal to F1 intersect G1 less F1. And usually on a good day, it's just the empty set. Okay. So therefore, as the other inclusion is evident, namely it's obvious that F1 is included in T cap, preimage under the T cap of F naught. Again, by the same token, because that's the union of the preimages under TF and TG, but the preimage under TF of F0 will be the whole F1 for sure, right? So F1 is contained here. It might be more because there might be some parts, there might be something in the intersection. There might be some edges from G1 that end in the intersection, so it can be strictly bigger. But this inclusion is obvious. And we just proved the other inclusion, right? Because now we proved that T cap preimage of F naught is inside F1, okay? So it's the other inclusion. And two inclusions give us equality. So F1 is equal to the preimage under T cap of F naught. And that's exactly the edge condition we're after, okay? And again, by the symmetric argument, we also have that G1 is equal to the preimage under T cap of G0. Okay? So summarizing, we have proved that the union is admissible. And by this, I mean the union of F with G is admissible. All right. And now the really new stuff, that's what we did in this semester. And I think this part of the reasoning I like most. Is that the same works for strong admissibility. Any questions so far? Okay, so it remains to prove that if the intersection is strongly admissible, then the union is strongly admissible. But note that it suffices to show that both G naught less F naught and F naught less G naught are unbroken. In the union graph. Right? Because strong admissibility means admissibility plus non-existence of breaking vertices. Okay? And so because we already proved, you see, strongly admissible implies admissible, admissible implies admissible. So all that remains to be proven is that this is unbroken, which means precisely that these two sets are unbroken in the union graph. That's all we have to prove. And it's fun. Yes. So to this end, suppose that V, which belongs to F0, is a breaking vertex for G naught less F naught in the union graph. Right, so maybe here it's good to make a picture. It's very similar to the picture we had before, but not the same. So here's my G naught less F naught, my F naught less G naught, and the intersection. Okay. So now we look at the set G naught less F naught to show that the inclusion of F in the union F union G is admissible, okay? Because then I take my F, I remove it from the union, I have then G naught less F naught, and this set must be unbroken. But I assume it is broken. I assume there is a breaking vertex, V, and the breaking vertex must be below this G naught less F naught, so it must be in F naught. Okay? This is what we wrote. But because it's a breaking vertex, okay, so then V emits infinitely many edges to G naught less F naught. So I don't know the beginning of this vertex yet, but surely I have infinitely many edges mapping into here. And don't think that they end in one vertex. They might end in one vertex, they might end in infinitely many vertices, that's finitely many vertices. Anyway, I have infinitely many edges coming from outside of this set into this set, from my vertex V. I didn't conclude yet where it is. But no, actually, I think I can say where it is, because it must be in F, all right, F0, so it's somewhere there. But it cannot be outside of the intersection set, because there are no, you see, this is what I argued before, there are no arrows which go from F naught less G naught into G naught less F naught. And the reason for this is, remember that such an edge cannot be in G1 because it doesn't begin in G1. But it also cannot be in F1 because it doesn't end in F1. So it's nowhere. So such an edge doesn't exist. Okay. So this means that my breaking vertex, even though I'm looking at a breaking vertex in the union graph, this breaking vertex must be in the intersection. Yeah, that's a very important conclusion. Okay. Yes. Okay. Ending in so V is in F naught intersect G naught. Okay. But that's not the end, of course. Also, we can observe that all these edges are in G1, right? Because they end outside of F0, so they must be in G1. Since they cannot be in F1, they must be in G1. Okay, so all these edges are in G1. Okay, now another thing which we know because of our assumption that V is a breaking vertex, so let me write it down like this. Furthermore, V emits at least one and at most finitely many edges ending beyond G naught less F naught, which means in F naught. Right? That's the idea of a breaking vertex. Into the set of interest, you should infinitely many edges, but outside the set of interest, you should finitely many and at least one edge. Okay? But now we don't know if it ends in F naught less G naught or in the intersection F naught with G naught. But now, if all of them end in F naught less G naught, these finitely many edges, so if all of them end in F naught in G naught, well, then they end outside of G naught, so they are not from G1, so they are all from F1. And now we violate the saturation property of F naught less G naught in F. Yeah. And they render F naught less G naught unsaturated in F, which is not allowed. Right? Because if I would have all these finitely many edges emitted from V outside of the set, if they all end in here, then they all must be in F1. And I have a situation where I have a vertex whose all edges in the graph F go from outside to this set into this set. This violates the saturation property. But this is not allowed because well, we have admissibility. So in particular, we have admissibility of the intersection graph in F. So this F naught less G naught must be saturated in F. Okay. So I can now draw an edge. There is at least one edge, which is inside F naught intersect G naught. It can be a loop, whatever. It can be more than one, but there is at least one which not only begins at V, but it ends in F naught G naught. But I'm behind my writing. Which is not allowed by the admissibility of the intersection in F, right? Okay, so therefore, V emits at least one edge call it E, ending in F naught intersect G naught. So this is my favorite edge E, and I repeat, it can be a loop. It's not important. If it's a loop, it still ends in F naught to G naught. F naught intersect G naught. Okay? But now, by the admissibility of the intersection graph viewed as a subgraph in G, so we are really using our resources, okay? I'm really using my assumptions. This is why I like this reasoning, because it really relies on what you assume. Okay, by the admissibility of F intersect G in G, now we have this edge condition. So we have that the preimage under the TG map of the set F naught intersect G naught, that's just equal to F1 intersect G1. All right. And of course, edge E is in here because it ends in this set. Okay. But this means that edge is in G1. So E is in G1. I'm not saying it's not in F1, but it's definitely in G1. Okay. Now there's one more thing to finish the reasoning. Also, since V emits finitely many edges, in the union graph ending in F naught, it also emits finitely many edges in G ending in the intersection. Right, this is because finiteness is a hereditary property in the category of sets. A subset of a finite set is finite. So if I restrict my edges just to G, and I restrict the ends of these edges just to the intersection, well, that's a subset. A subset of a finite set is finite. And we know that it's non-empty because we already have E inside. Okay? So all this together makes V a breaking vertex for G naught less F naught in G. Okay? Because I have infinitely many edges in G, mapping from V to this set, from outside of this set. And then I have finitely many and at least one edge also in G, mapping from V, but now outside of the set. So this is the definition of a breaking vertex in the graph G for this set. And we are done. So we got a contradiction because, of course, strong admissibility means that this set must be unbroken in G, right? So therefore, our assumption about the existence of a breaking vertex was false. Where is it? Right, so such a vertex does not exist. So this means that the set G naught less F naught is unbroken in the union graph. And as before, by maybe let's write it down. Hence, G naught less F naught is unbroken in the union graph. Okay, by reversing the reasoning. Yeah, we proved that if it is broken in the union graph, then it is broken in G. And because we assume it's not broken in G, it is not broken in the union graph. And of course, to end the proof, as before, the symmetric argument which interchanges the roles of F and G shows that also F naught less G naught is unbroken in the union. And this ends the proof. Okay? Ooh la la. But okay, the main thing is done. This was the highlight of the whole semester. We proved a theorem, which is very recent and which I hope I can convince you next semester is also very useful. And I repeat, if you have to remember only one thing from this semester, that's the thing to remember, this theorem. Yeah, Jacek?
I have a question about the
Sure.
proof. Could you say once again why E belongs to G1?
Okay, E belongs to G1 because of this condition, right? This is the edge condition for the admissibility of F intersection G in G, okay?
Yes, this I can see, but
So you agree with this equality, right?
yes.
Now, E is an edge which ends here, right? So if I take the preimage of this under this map, I know that this edge, so let me put it this way.
So my question would be, but do we know that, well, we are taking preimage with respect to the map TG, but do we know that E does, well, E could belong, comes from the graph F?
No, that would contradict this edge condition. So let's see it. This is the intersection, and this is the whole graph G, okay? And now I view the intersection graph as a subgraph in G, okay? And, wait a second.
Piotr, is it
Yes?
about the equality? Is it about the equality?
You know, I mean, the thing is that I jumped into the conclusion that TG of E must be in F naught intersect G naught. But Jacek is right that there is a problem here, because what I know is that T cap of E is in F naught G naught. Oh, so sorry, Houston, we have a problem. I see the gap now.
So you don't know if G is hereditary in F union G.
Wait. Well, in fact, we can forget edges going here because, as you just mentioned, we have also hereditary property. No. Sorry, hereditary is something else. This is hereditary for this set. No. That's hereditary. I don't see how it helps. So what would happen if this edge was in F1?
But Piotr, I mean, like, did we assume that not only F intersect G is admissible in F, but did we also assume that F itself is hereditary in F union G?
Well, we didn't assume that it is hereditary. We proved it that it's hereditary in F union G. But this is right. F is hereditary. Yeah, F is hereditary in F union G, but how does it help us? It means that, it means that F hereditary in F union G, it means, sorry, but you cannot say F. I mean, if you have F as admissible in F union G, that this means that this set, G naught less F naught, is hereditary in the union. So I don't see how it helps, Alex. It's completely irrelevant.
I can't see
Irrelevant.
really like the.
I'm not looking at edges emitted from here. I'm also not
I
looking
can't
at
really
edges
see
emitted
the.
from there. So it's completely irrelevant, hereditary.
I just can't really see the picture.
Well, you have an edge E, which is emitted from the intersection, and it ends in the intersection. And I want to claim that such edges must be in G1. But, and I wanted to use this admissibility, this equation, okay? But you know, if E is not in G1, then of course, T cap of E is just TF, so that's irrelevant, okay? But maybe, okay, let's try to do it this way, all right? So this is definitely true. So T cap preimage of F naught. So V is in T cap preimage of F naught G naught, but this is the union. This is the union of T F preimage F naught G naught with TG preimage F naught G naught. Right, Jacek? Agree?
Yes.
Okay. But using the admissibility of both, so simply the admissibility of the intersection, okay? We know that this must be F1 G1 and this must be F1 G1. So this is the union of F1 intersect G1 with F1 intersect G1. Agreed?
Yeah, this is nice, and this gives us what we want.
Yeah, but you gave me a scare. But you're right, you found a gap, and we just fixed it. Yeah, it's because I really know only this, and right, but this is tantamount to V being in the preimage of T cap. But this means that V is in this union set. But I now use both admissibility conditions for F intersect G in F and for F intersect G in G. And here, in both cases, we must just get F1 intersect G1. So this is F1 intersect G1, and E is in here, so E is in G1. Thank you. That's why I like teaching or giving lectures. Wow, this is really cool. This is really cool. Yes. Sorry about the mess. I'll correct it in the lecture notes. So it's even better because the reasoning is more subtle than we thought it would be. But the conclusion stands, right? We have that E is in G1, and all these edges emitted from V that end in this intersection must be in G1, all of them. So this means that V is really a breaking vertex for G naught less F naught in G. Okay. Wow. What an amount of adrenaline. Is everybody else happy? Any other gaps? Please shoot at will. Nobody? Okay. All right. Boom. We have only 10 minutes left. And now I wonder which way to proceed. I will now be very sketchy, but the lecture notes are written. I would like to do two things very quickly. Well, actually three, but let's see how much we manage. The third one can go into the recitation class. So I'm afraid I'll have to skip examples of graph homomorphisms. So that's the highlight. That's the cherry on the cake. And this is what officially ends the semester. That's the peak. We have climbed it and put our flag there, right? But now there are still some, photos we want to take around panorama. And well, actually, this is not related to it, but there are two more things in the graph theory which I will need very much so in the next semester. So I'd like to, because they are purely graph theoretic, I would like to do them at least very quickly in this semester. So let me grab a bigger piece of chalk. So first, there's the concept of the extended graph. So those of you who know Leavitt-Pav algebras, those of you who attended Oscar's talk on Friday, you know what I'm talking about. But for any graph E, take it as a definition. It is at the beginning of a lecture note. The extended graph can be most briefly defined. Extended graph E bar can be defined as the gluing of E over the set of vertices E naught with E opposite. Okay, so what I do, I take my graph E, I leave the vertices alone, I double the set of edges, and I declare that to every edge in E, I have a ghost arrow going in the opposite direction. Okay, so that's the extended graph. Yeah, yes, but you see, the thing is that we don't care about it. This is very important because when you want to see Leavitt-Pav algebras or graph sister algebras as constructed from path algebras, then you must go through the extended graph. Because you take the path algebra and then you divide it by the Kunstkrieger ideal in the path algebra, okay? But whenever you do graph algebras, you never ever write the adjoints because you see, this is just the star operation. If I have an edge in E1, it gives me some partial isometry as X. And if you want, I take the star of it, which I can think of as S of X star. But that's, you can view it just as a notation.
So by the way, in this case, you have this two points, right? So you have one arrow and the opposite arrow.
Yeah, but I don't know why you would want to call it a group point.
Well, you asked me at the beginning, this is similar like a group point and not a group point, not that is not inverse. So not that is inverse of previous.
Well, yeah, but it's not quite. This is not, because you see, it's not like this is really the inverse, it's an adjoint operator. And it doesn't mean that Sx star is the inverse of Sx. It is not. This is not the unitary. It's a partial isometry. So this is nothing like this. So this is not a groupoid. If I have an arrow and the ghost arrow, it's not like this arrow is the inverse of this arrow. This is completely wrong. That's not the case. It is the case when you have a loop and one vertex. Then indeed, then the dotted arrow is the inverse of the arrow. But in a very special case. In general, it is not. That's really the adjoint. And vertices are self-adjoint elements. They are projections. Okay, so this is a crucial definition. And another crucial definition for which I prepared many examples, but I'll not be able to do them. Well, maybe at least some of them I'll do them. Is what is a homomorphism of graphs? A homomorphism from a graph E to a graph F is a pair F naught F1, where F naught is a map from E naught to F naught. I mean, lowercase f naught is a map from E naught to capital F naught. And likewise, F1 is a map from E1 to capital F1. And these are maps, just usual spherical maps. Rendering the following diagram commutative. And the diagram is as follows. Here you have E1, you map it by F1 to capital F1. But here we're rendering the diagrams because there are two of them. Here I can go by the source map in E to E0. Here I can go by the source map in F to F0, but now we can join E0 and F0 by F0. And the same for the target maps. So E1 mapping to F1, E0 mapping to F0, and now the target maps. TE going from E1 to E0, and TF going from F1 to F0. So rendering the diagrams commutative. And with this definition of a morphism, we can now consider the category of graphs. This is the most naive approach to having a category of graphs, but it was spectacularly effective in the studies of, I think, subgroups of three groups. There's a celebrated paper of Stallings in Invenciones, where he proved something extraordinary in the theory of groups by using exactly thus obtained category of graphs. Somehow it turned out that in order to understand and prove something in groups, you can translate it into a problem in graphs where you can do it. And this is a very famous paper from Invenciones. So this was very useful. Yeah? Graphs are useful not only in graph algebras and K-theory of sister algebras. They're also useful in other areas of mathematics. By the way, you'll all get an announcement soon, but this Wednesday, we will have an absolutely spectacular talk at our NCG seminar, because it will be about classification of graph sister algebras. And this is a fundamental topic. I mean, this is the next logical step after the famous Elliott's classification of sister algebras. Now, in order to have at least some first go at the classification of non-simple sister algebras, well, we look at graph sister algebras. Yeah. And Soren Ehlers, our speaker, is one of the best people in the world when it comes to graph algebras. So I strongly urge you to come on Wednesday to this talk. I'll send you an announcement, if not today, then tomorrow. Yeah, well, I have 1 minute left. That's not so much to show examples, but you see, let me just make a point. So on one hand side, for the sake of graph algebras, this definition is too restrictive because we must allow mapping edges to paths, not just to edges. But on the other hand, it's too relaxed because I can give you many funny maps that would not produce any morphisms at the level of graph algebras. I mean, for instance, you get, of course, any inclusion of the subgraph in a graph will give you a homomorphism, okay? That's obvious. So inclusion is a homomorphism of graphs. But you can do other things. For instance, you can have two loops at one vertex, and you can map it into a graph when you have just one loop at one vertex, just by identifying two loops. That's okay. It satisfies this condition, all right? But it doesn't mean that it's useful for graph algebras. So one of the reasons of our adventure is to redefine the category of graphs to suit the needs of Levitt graph algebras and graph algebras. But that's the next semester. For the time being, thank you very much. We resume in 15 minutes. We'll have 45 minutes of recitation class. We have 3 quick exercises to do. And also, I have a comment about answering my question from the lecture. But let's do it after a break. I think we deserve to have a 15-minute break. Okay? Thank you. I stop recording.